All right, let's dive into a story that proves the biggest game changers aren't always the loudest explosions or the most glamorous machines. Sometimes victory is brewed in a refinery, bottled in a drum, and flows, literally, through the veins of a nation's war machine. Get ready, because what I'm about to tell you about will completely reframe how you think about air superiority in World War II. Imagine, it's early 1944. The skies over Europe are a brutal, unforgiving battlefield. The roar of Merlin engines, the rattle of machine guns, the terrifying dance of steel and fire. This is the daily reality for fighter pilots. And at the heart of this aerial ballet, the American P-51 Mustang had already earned its fearsome reputation. Long-ranged, agile, and a deadly adversary, it was the bomber's best friend, the Luftwaffe's worst nightmare. But what if I told you that the Mustang, this already legendary aircraft, was about to undergo a metamorphosis so profound, so unexpected, that it would permanently shatter the German war machine's will to fight? What if the key to its transformation wasn't a new engine, a stealthier design, or even a more lethal weapon system, but a secret weapon, dyed a distinctive shade of purple, flowing unseen through its fuel lines? This isn't a story about daring dogfights alone, or the genius of aircraft designers. This is the untold saga of how a seemingly mundane substance, aviation fuel, became the ultimate strategic advantage, turning already formidable Allied fighters into aerial demons capable of performances the Germans simply could not comprehend, let alone counter. It's a testament to the quiet heroes in laboratories and refineries, whose innovations ensured that the brave pilots in the cockpit had an insurmountable edge, day after day, sortie after sortie. Rewind to a moment frozen in time. Dayton, Ohio, early 1944. A test pilot, calm amidst the contained fury, grips the throttle of a P-51B Mustang. His mission: push the boundaries, breach the accepted limits of what this magnificent machine could do. He shoves the throttle forward, past the standard war emergency power setting, into uncharted territory. The engine doesn't just roar. It howls, a primal scream of unleashed power. Boost pressure climbs, rapidly hitting an unprecedented 75 inches of mercury. This phenomenal surge isn't just about the engine. It's about what's feeding it. A new, experimental fuel, simply code-named Grade 150. The airspeed indicator needle swings wildly, sweeping past numbers that represented the absolute zenith of what Allied fighters had ever achieved. At 25,000 feet, the Mustang isn't just fast, it's accelerating through 448 miles per hour. On the ground, engineers, their faces etched with a mixture of disbelief and exhilaration, exchange stunned glances. The radio crackles, a pilot's voice, steady but undeniably awed, confirms the impossible. This wasn't a minor tweak, a slight bump in performance. This was a seismic shift, a revolution. A purple-dyed aviation gasoline had just rewritten the rules of aerial combat. A chemical advantage so utterly profound, it would obliterate every single assumption the formidable Luftwaffe held about American fighter capabilities. They thought they knew the enemy. They were about to discover a monster they hadn't even imagined. The war in Europe, already a bloody grind, was about to take a decisive turn. And the unexpected catalyst wasn't a radical new aircraft design, a brilliant tactical gambit, or a daring new weapon. It was a liquid. A fuel that allowed existing fighters to perform at levels that simply defied German expectations. What the German High Command, the brilliant engineers of the Third Reich, and the battle-hardened pilots of the Luftwaffe did not yet know was that American and British fuel chemists, working tirelessly in labs far from the front lines, had achieved something their own synthetic fuel program for all its technical ingenuity, could never hope to match. While German fighters were struggling with a B-4 fuel, rated at a modest 91 octane, and their absolute best C-3 fuel barely approached the equivalent of the Allied 130 grade fuel, American refineries were churning out aviation gasoline with a performance number of 150. The implications were staggering, almost unfathomable. Think about it. A P-51 Mustang, powered by the standard 130 grade fuel, could hit a respectable 437 mph at 25,000 feet. Impressive, right? But the exact same aircraft, flown by the exact same pilot, at the exact same altitude, running on this new 150 grade fuel, could exceed 448 mph, even nudging 490 mph in certain configurations, a performance jump of 25 to 30 miles per hour. In the high-stakes game of aerial combat, that's not just an edge, that's the difference between life and death. That's the difference between escaping with your life and becoming another statistic. German fighter pilots, who had learned to grudgingly respect the Mustang's incredible range and high-altitude performance, were about to discover that the Americans had fundamentally altered the entire equation of aerial combat. The Messerschmitt Bf-109G, the Luftwaffe's frontline fighter in early 1944, had a maximum speed of around 400 mph at altitude. The Focke-Wulf FW-190A, another potent adversary, could reach 400 mph under optimal conditions. Against Mustangs running on 130 grade fuel, German pilots at least had a fighting chance. They could attempt engagements on favorable terms, using their superior dive speed or cunning maneuvers to gain an advantage. But against Mustangs, Spitfires, and Tempests running on 150 grade fuel, German fighters were operating at a fundamental, inescapable disadvantage that no amount of pilot skill, no tactical brilliance, no daring aerial maneuver could possibly overcome. They were slower. Period. And in the skies, speed is king. Speed allows you to choose the fight, dictate the terms, or escape if necessary. Without it, you are simply prey. This incredible advantage, this purple potion that transformed warbirds, didn't spring from the crucible of war, birthed from some desperate, last-ditch effort. No, the story of how this came to be begins much earlier, with the painstaking, often unnoticed, peacetime work of petroleum chemists. These unsung heroes understood a fundamental principle that would ultimately decide the fate of nations: the octane rating of fuel. In simple terms, octane measures how much an air-fuel mixture can be compressed before it spontaneously detonates, before it explodes prematurely in an uncontrolled fashion. Think of it like a coiled spring. The more tightly you can compress that spring before it snaps, the more energy it can release in a controlled burst. In an engine, higher compression ratios mean more power from each controlled combustion cycle. More power means faster aircraft, higher operational ceilings, and the ability to climb like a rocket. The science was straightforward, elegantly simple in its premise, but the engineering required to produce high-octane aviation fuel at an industrial scale was extraordinarily complex, a monumental challenge that only a handful of nations could truly meet. In 1940, as the war raged like a wildfire across Europe, American aviation fuel production was largely centered on a modest 87-octane gasoline. This was perfectly adequate for commercial aviation, for the leisurely flights of the pre-war era, and for early military trainers. But it was woefully, dangerously insufficient for the high-performance combat aircraft that were now duking it out above the battlefields of Europe. It was at this critical juncture that the British, staring down the barrel of the Luftwaffe's superior numbers, and desperately searching for any advantage, threw their lot in with American oil companies. Their goal? Develop 100-octane fuel. This concentrated effort bore fruit just in time for the Battle of Britain, a pivotal moment when the fate of an island nation hung by a thread. The difference was immediately, dramatically apparent. British Spitfires and Hurricanes, now powered by this new 100-octane fuel, suddenly gained an additional 30 to 40 miles per hour in speed at altitude. Their climb rates, a crucial metric in intercepting bombers, soared by 500 to 1,000 feet per minute. German pilots, who had previously enjoyed clear performance advantages with their 91 to 100-octane fuel, suddenly found themselves on even terms, then quickly at a disadvantage. It was a rude awakening, a clear signal that the technological race was far from over. The development of 130-grade fuel provided yet another monumental leap forward. This fuel, with its performance number of 130 on rich mixture settings, became the very backbone of Allied air power throughout 1943. It fueled the legendary Merlin engines, not just in Spitfires, but also in the newly emerging P-51 Mustangs. It powered the Allison engines in the twin-boomed P-38 Lightnings and the massive Pratt & Whitney R2800 radial engines that gave the P-47 Thunderbolts their raw power. Production of this critical fuel scaled rapidly, driven by the visionary leadership of pioneering aviation fuel advocate General James Doolittle, a man who, in the seemingly peaceful 1930s, had tirelessly worked to convince both a skeptical military and hesitant oil companies to invest heavily in high-octane fuel development, recognizing its crucial future role. Doolittle was a prophet in an era that struggled to grasp the future of air power, battling against entrenched conservatism and short-sighted economics. His relentless advocacy during peacetime now paid dividends in the crucible of total war. By 1943, a staggering 17 Allied refineries were producing high-octane aviation gasoline, leveraging the catalytic cracking process perfected by the brilliant French émigré engineer Eugène Houdry. This wasn't just about making good fuel, it was about making vast quantities of good fuel. American refineries alone were churning out millions of gallons monthly, an industrial torrent sufficient to fuel the massive bomber offensive against Germany and sustain the growing fighter forces that protected those vulnerable giants. German fuel production, by stark contrast, remained an Achilles' heel, bottlenecked by their reliance on synthetic fuel derived from coal. The Burgess process, a technically sound method for converting Germany's abundant coal reserves into aviation gasoline, was slow, incredibly resource-intensive, and inherently fragile. Even at peak production, Germany could only manage to produce a mere fraction of the high-octane fuel that flowed ceaselessly from American refineries. Most German fighters, the venerable Bf-109s and the powerful Fw-190s, flew on B-4 fuel, rated at approximately 91 octane on the lean mixture scale. Their premium C3 fuel, primarily reserved for the BMW 801-powered Focke-Wulf 190s and select Messerschmitt variants, was roughly equivalent to Allied 100-octane or early 130-grade fuel, but it was available in far more limited, precious quantities. By 1944, perhaps two-thirds of German aviation fuel production was C3 grade, but even this represented a tiny fraction of what the Allies were producing. It was a case study in strategic resource disparity, where Germany's inherent disadvantages were amplified by an inability to innovate and scale at the same pace as the Allies. To truly appreciate the genius of 150-grade fuel, we need to delve a little deeper into the fundamental principle of internal combustion engines. Octane ratings, as we've discussed, measure detonation resistance. Picture this. When a piston compresses the air-fuel mixture in the cylinder during the compression stroke, both temperature and pressure skyrocket dramatically. If the fuel spontaneously ignites before the spark plug fires, the result is detonation. This isn't a controlled burn, a smooth, powerful push. It's an uncontrolled explosion, a violent, shockwave-inducing event that can damage or even outright destroy engine components. It's like hitting your engine with a hammer from the inside. Higher octane ratings, therefore, mean the fuel can withstand significantly higher compression without detonating. It can take the heat and the pressure without spontaneously combusting, allowing engineers to design engines with higher compression ratios, squeezing out every last ounce of power. Here's where it gets interesting. Octane ratings, by definition, cannot exceed 100. Why? Because 100 octane represents the detonation resistance equivalent to pure isooctane, which is the reference standard. So how do you get 150 grade fuel? This is where performance numbers come into play. Performance numbers measure how much better than pure isooctane a fuel can perform, particularly under rich mixture, high-power conditions. A fuel with a performance number of 150 means it can withstand 50% more compression than pure isooctane before detonating. It's a chemical superpower, allowing engines to be pushed far beyond their designed limits with unprecedented reliability. Creating such a marvel of chemistry required more than just refined crude oil. It demanded the precise addition of anti-knock compounds, primarily tetraethyl lead, a potent but also highly toxic additive. This was blended meticulously with specific aromatic hydrocarbons like toluene and xylene, creating a base gasoline with unparalleled resistance to premature ignition. British fuel chemists at the Royal Aircraft Establishment, a veritable think tank of wartime innovation, relentlessly tested countless blends throughout 1942 and 1943. They sought the optimal combination: maximum anti-knock performance, high energy content, and crucially, manufacturing practicality. It had to be mass-producible. American researchers at Wright Field conducted parallel investigations, sharing invaluable data with their British counterparts in a truly transatlantic scientific effort. By early 1943, both nations had successfully produced experimental batches of what they designated as 150 grade fuel. The designation, as you might guess, was slightly misleading. It didn't mean it had an octane rating of 150, which was chemically impossible. What it actually meant was a fuel with a performance number of 150 on the rich mixture scale, combined with 100 octane performance on the lean mixture scale. This dual capability was revolutionary: efficient cruising for range, brutal power for combat. This new fuel, easily identifiable by its distinctive purple dye, underwent extensive testing throughout 1943, and the results, frankly, exceeded all expectations. Merlin engines, the heart of the P-51 Mustang and the Spitfire, running on 150 grade fuel, could sustain manifold pressure readings of an astounding 75 inches of mercury, compared to 67 inches on the already excellent 130 grade fuel. What does that mouthful of technical jargon actually mean? It translates directly into a colossal increase in horsepower. A Packard Merlin V, the engine that powered the iconic P-51D Mustang, generated 1,490 horsepower at standard military power on 130 grade fuel. The same exact engine, running on 150 grade fuel at war emergency power settings, generated an astonishing 1,720 horsepower. In the P-51B, with its V1650-3 Merlin variant, the power increase pushed output to approximately 1,600 horsepower. That's a jump of over 200 horsepower in an already powerful engine, without changing a single physical component of the engine itself. Flight testing at Wright Field unequivocally confirmed that these performance gains were substantial across all flight regimes. Maximum speed increased by approximately 25 to 30 km/h at altitude. Climb rates improved by several hundred feet per minute. Most importantly, and this is the critical detail, these monumental improvements came with no modifications whatsoever to the aircraft itself. The same Mustang, flown one day on 130-grade fuel and the next on 150-grade fuel, became measurably faster, more powerful, and more capable, simply because of the magical purple liquid flowing through its fuel lines. It was a stealth upgrade, undetectable from the outside, but absolutely transformative on the inside. The decision to introduce 150-grade fuel to operational fighter squadrons was made in early 1944. The timing was meticulously calculated, strategically brilliant. The 8th Air Force, based in England and conducting audacious daylight strategic bombing raids deep into the heart of Germany, was suffering unsustainable losses. Despite the arrival of the first P-51 Mustangs in December 1943, German fighter forces were still inflicting heavy casualties on American bomber formations. The losses were not just in aircraft, but in invaluable, highly trained air crews. What American planners desperately needed was not just an escort fighter with long range. The Mustang already provided that. They needed an escort fighter so fast, so utterly dominant, that German interceptors could not easily escape or refuse combat on unfavorable terms. They needed a wolf, not just a guard dog. In May 1944, the first operational deliveries of 150-grade fuel arrived in England. Distribution was, understandably, carefully controlled, almost secretive. Not every fighter group received the new fuel immediately. The 8th Air Force began with select squadrons, both to manage the intricate supply logistics of a totally new fuel type and to rigorously evaluate its combat performance under real-world conditions. The British Royal Air Force, which had pioneered much of the early testing and understood its potential perhaps better than anyone, also began equipping its fighter squadrons with the new fuel. Priority went to units tasked with the most critical high-speed interception missions, particularly those hunting the dreaded German V-1 flying bombs, which were beginning to terrorize London in June 1944. These V-1s, terrifying jet-propelled missiles, flew at approximately 400 km/h at relatively low altitudes. Intercepting these fast-moving, unpiloted weapons required fighter aircraft capable of matching or exceeding that speed at sea level or low altitude, where the denser air typically reduced the performance of all aircraft. Hawker Tempests and Spitfire. Teens, already among the fastest piston-engine fighters, could barely catch the V-1s. Mustangs running standard fuel were marginal, often requiring dangerous dive tactics. But Mustangs running on 150-grade fuel suddenly had the crucial speed margin to intercept reliably. This wasn't just about dogfighting. It was about saving civilian lives, protecting entire cities from a new form of terror. A legendary example of this newfound capability occurred on June 18, 1944. Major R.E. Turner of the 356th Fighter Squadron, flying his P-51, encountered a V-1 flying bomb. Instead of shooting it down, a dangerous prospect with an exploding warhead, he deployed an audacious, incredibly precise technique. He destroyed the V-1 by actually tipping its wing with his P-51's wingtip. This maneuver, requiring exceptional speed and precision to position the fighter's wingtip within 6 inches of the V-1's wing surface, then using the turbulent airflow to roll the flying bomb off course and send it crashing harmlessly into unpopulated areas, was a testament to the Mustang's enhanced control and speed. It was a feat of aerial ballet made possible only by the performance boost of the new fuel, and it would be used successfully at least 16 times during the campaign. The first widespread combat use of 150-grade fuel by American P-51 pilots coincided with one of the most pivotal moments in history: the Normandy invasion in June 1944. Fighter groups of the 8th Air Force, tasked with achieving and maintaining absolute air superiority over the invasion beaches, a task vital for the success of the entire operation, flew continuous combat air patrols and bomber escorts using the new purple-dyed fuel. It didn't take long for the reports to start filtering back to German intelligence. German fighter pilots, facing an onslaught of Allied aircraft, began reporting encounters with Mustangs that performed beyond anything they had previously experienced. These weren't just fast, they were implausibly fast. Luftwaffe intelligence officers meticulously collected these pilot reports, describing American fighters that could not be caught in any flight regime, that could accelerate away from German interceptors with disconcerting ease, and that seemed to possess power reserves that defied all conventional explanation. Initially, these reports were largely dismissed. Pilot error, the intelligence officers reasoned. Exaggeration. Our pilots are tired, outnumbered, facing mounting losses. Their reports of superior American fighter performance are surely the result of stress and fatigue, not actual performance increases. This assessment, based on logic that failed to account for a hidden variable, was fundamentally, tragically wrong. But the devastating truth, the true nature of this chemical ghost in the machine, would not become fully clear until after the war, when the wreckage had been cleared and the secrets unveiled. One of the most compelling pieces of evidence came from the very top. Adolf Galland, a legendary Luftwaffe ace with 275 victories, mostly achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews conducted during the 1970s and 1980s, Galland spoke candidly about his encounters with late-war Mustangs. He recalled being genuinely shocked at the performance of American fighters during the final year of the war. Galland, who would later test fly captured American fighters, including the P-51, P-47, and P-38, noted that the Mustang, in particular, deeply impressed him with its incredible speed, its brutal climb capability, and its stellar high-altitude performance. What Galland and other German pilots did not realize during those desperate combat engagements was that they were facing an aircraft whose performance had been chemically enhanced, pushed far beyond its original designed specifications, operating at power settings that the original Mustang engineers at North American Aviation and Rolls-Royce had never even envisioned as sustainable. The Merlin engine, designed by Rolls-Royce and produced under license by Packard in the U.S., had been engineered with meticulous attention to thermal limits, bearing loads, and detonation margins. Running an engine at higher boost pressures pushes all of these parameters closer to their absolute breaking points. What made 150-grade fuel truly revolutionary was that it allowed engines to operate at these extreme settings, right on the knife edge of destruction, without the catastrophic detonation that would have instantly destroyed engines running lower-grade fuels at the same boost pressures. The intricate chemistry behind this capability involved the complex interaction of fuel molecules, air molecules, heat, and pressure inside the engine's combustion chamber. Tetraethyl lead, the primary anti-knock additive, worked by interfering with the chemical chain reactions that led to spontaneous, uncontrolled ignition. But, as with almost all technological advancements, there were trade-offs. Tetraethyl lead was, and still is, highly toxic, requiring extremely careful handling by ground crews. It left corrosive deposits on spark plugs, valves, and cylinder walls, significantly increasing maintenance requirements. 150-grade fuel, with its very high lead content, exacerbated these maintenance issues, accelerating wear and tear. Fighter groups using the new fuel quickly experienced more frequent spark plug fouling and increased cylinder wear. American maintenance procedures, however, adapted with remarkable speed and ingenuity. Spark plug replacement intervals were shortened, cylinder inspections became more frequent, and engine overhaul schedules were adjusted. The performance gains were universally judged to be worth the increased maintenance burden, a small price to pay for such a decisive advantage. For the pilots themselves, the transition to 150-grade fuel required new operating procedures and a refined understanding of their aircraft's capabilities. Manifold pressure limits were raised, giving them access to unprecedented power. Pilots had to be exquisitely careful not to overboost their engines, particularly at low altitudes where air density was highest and the engine could be pushed too far, too fast. Most significantly, pilots had to learn to manage fuel consumption with greater precision than ever before. 150-grade fuel provided more power, yes, but running at maximum boost consumed fuel at an alarming rate. Escort missions deep into Germany, to Berlin and back, already pushed the Mustang's range to its absolute limits. Utilizing the new fuel's full capability meant careful, conscious fuel management, knowing exactly when to use maximum power for combat advantage and when to throttle back for cruise efficiency to ensure a safe return. Combat reports from the summer and fall of 1944 paint a vivid picture of this transformation. 8th Air Force fighter groups equipped with the new fuel reported significantly higher victory-to-loss ratios and a dramatically increased ability to intercept German fighters attempting to attack bomber formations. German fighters that had previously been able to make fast, slashing attacks and then escape with impunity now found themselves unable to outrun pursuing Mustangs. The hunter had become the hunted. Consider the real-life encounter on August 6, 1944. Lieutenant Hollis Bud Nayland of the 357th Fighter Group was flying as part of Operation Frantic, daring missions to Soviet air bases. Over Eastern Europe, Nayland encountered German fighters. Flying his P-51D, appropriately named Hellsbells, and powered by the new 150-grade fuel, Nayland engaged a Messerschmitt Bf 109 flown by German pilot Josef Schick. In the ensuing combat, Nayland's speed advantage, courtesy of that purple liquid, proved decisive. He closed rapidly on Schick's aircraft, a relentless predator, and fired a burst that damaged the German fighter's cooling system. Low on fuel and ammunition after the intense engagement, Nayland, exhibiting a flash of airman's camaraderie, broke off pursuit and waved to the crippled German pilot before returning to escort duties. Schick, against all odds, managed to belly land his aircraft near German lines. For 40 years, Schick wondered why the American pilot had not finished him off, never realizing that Nayland had believed he had merely damaged, rather than effectively destroyed, the aircraft. When historians later connected the two pilots and arranged a meeting in Germany, Schick, a man of profound integrity, openly acknowledged that the American's Mustang had demonstrated performance that exceeded anything he had previously encountered in combat. The speed with which Nayland had closed, the sheer power reserves evident in the engagement, had been unlike any previous combats with American fighters. It was a tangible, undeniable edge that stuck in his memory for decades. The psychological effect on Luftwaffe pilots was devastating. Already outnumbered and facing overwhelming Allied numerical superiority, they now confronted American fighters that seemed to possess unlimited performance margins, a seemingly endless wellspring of speed and power. Their tactical options narrowed dramatically, leading to a profound sense of helplessness. They could attempt mass attacks, hoping that sheer numbers would overwhelm the escorts, often a suicidal proposition. They could refuse combat entirely, preserving their precious aircraft and pilots, but effectively ceding control of the skies and abandoning their homeland to relentless bomber attacks. Or they could engage and, most likely, be shot down by Mustangs that were demonstrably faster, more maneuverable, and flown by American pilots who were growing increasingly confident, aggressive, and assured of their technological superiority. Reich Marshal Hermann Göring, the arrogant and often deluded commander of the Luftwaffe, famously remarked, upon seeing P-51 Mustangs flying with impunity over Berlin, that he knew the war was lost. This wasn't just a casual comment. It reflected the Luftwaffe's profound strategic dilemma. The Mustang's unprecedented long range meant that nowhere in Germany was safe from American daylight bombing raids, a constant crushing pressure on German industry and morale. The introduction of the superior 150-grade fuel in mid-1944 deepened this crisis, turning an already desperate situation into an existential nightmare. Luftwaffe technical intelligence eventually, though too late, obtained samples of Allied 150-grade fuel from captured drop tanks or crashed aircraft. German fuel chemists, world-renowned in their own right, meticulously analyzed the samples and confirmed what Luftwaffe pilots had been reporting in increasingly frantic tones. The Americans had indeed developed aviation gasoline with performance characteristics far beyond anything German synthetic fuel plants could produce at scale. While some German sources suggested that late-war C3 fuel approached performance numbers of 150, its production was severely limited, and its quality was notoriously inconsistent. To add insult to injury, the relentless Allied bombing of German synthetic fuel plants, particularly the devastating raids on Leuna and other major facilities in May and June 1944, further choked off German fuel production, turning a trickle into a drip. By late 1944, the Luftwaffe was desperately rationing fuel. Fighter units received priority, yes, but even they operated under increasingly tight constraints, often limited to a single sortie a day, or even less. Training for new pilots was cut back severely, creating a catastrophic shortage of experienced airmen. Many German pilots reached operational units with minimal flying experience, a stark contrast to American pilots who typically had several hundred hours of intensive training before entering the terrifying crucible of combat. This wasn't just a technical disadvantage, it was a systemic collapse. The numbers tell a stark story of triumph and tragedy. Between January and May 1944, before the widespread introduction of 150-grade fuel, American bombers suffered loss rates of approximately 3 to 6% per mission. These were sustainable, perhaps, but they were deeply painful, costly losses in both machines and men. But then a seismic shift occurred between June and December 1944. After the introduction of 150-grade fuel and the resultant achievement of decisive air superiority, bomber loss rates plummeted to under 2% per mission. Fighter victories, by contrast, increased dramatically. American P-51 groups across the 8th, 9th, and 15th Air Forces claimed approximately 4,950 German aircraft destroyed in air-to-air combat between late 1943 and May 1945, with a significant, indeed overwhelming, portion of those victories coming after June 1944. The German pilot force, which had entered 1944 with substantial experience despite heavy losses on the Eastern Front, was systematically, brutally destroyed. By D-Day, June 6, 1944, only 2 Luftwaffe aircraft were able to appear over the Normandy beaches, a testament to their crippling impotence. The Luftwaffe still possessed thousands of fighters, on paper, but they tragically lacked the fuel, the properly trained pilots, and the tactical flexibility to use them effectively. The chemical advantage had effectively grounded a once mighty air force. Let's briefly revisit the technical specifications of 150-grade fuel, because they are crucial to understanding its impact. The fuel's lean mixture octane rating of 100 meant it resisted detonation as well as pure isooctane when engines ran at cruising power settings, ensuring efficient long-range flight. But its rich mixture performance number of 150 meant it could withstand 50% more compression than isooctane when engines ran at maximum power. This ingenious combination allowed pilots to cruise efficiently for maximum range, conserving precious fuel, then switch instantly to rich mixtures at high power for combat, confident that their engines would not detonate even at the most extreme boost pressures. It was like having two engines in one, a cruiser and a drag racer. The handling procedures for 150-grade fuel, as mentioned, required special precautions due to its high tetraethyl lead content. Ground crews, the unsung heroes who serviced these machines, wore protective equipment when fueling aircraft. Spills were cleaned up immediately to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent accidental mixing of fuel grades. Despite these precautions and the inherent toxicity, the safety record was remarkably good. Industrial accidents directly attributable to the fuel were rare, a credit to the rigorous safety protocols implemented by the Allies. The transition in operational squadrons required extensive pilot training. Pilots received detailed briefings on the new fuel's properties and updated engine operating procedures. Manifold pressure limits were raised, and operational guidelines specified precisely when and how to use maximum power settings. Crucially, the aircraft themselves required no modifications. The engines, fuel systems, and all components were fully compatible with both grades, simplifying logistics and operations immensely. A strategic masterstroke of compatibility. The production statistics tell a story of industrial mobilization on a scale that Germany, despite its initial advantages, simply could not match. Between May 1944 and April 1945, the 8th Air Force alone consumed over 53 million gallons of 150-grade fuel. Allied production across all refineries likely exceeded 200 million gallons during its operational use. Each gallon of this precious purple liquid required a vast refining infrastructure, specialized chemical additives, including toxic tetraethyl lead, rigorous quality control testing, transportation across the Atlantic to Europe, secure storage in massive facilities, and meticulous distribution to dozens of airfields. American industrial capacity in 1944 operated at levels that seemed almost miraculous. Factories produced bombers by the thousands, fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades. This wasn't just luck. It resulted from decades of industrial development, vast natural resources, a protected homeland safe from enemy bombers, and a dedicated workforce that included millions of women who stepped into factory jobs, not just to support the war effort, but to ensure its ultimate success. The Royal Air Force, deeply involved in the early testing and fully aware of its potential, also used 150-grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire Mach 14s, Tempest 5s, and Mustang 3s and IVs received priority allocation of the new fuel. RAF pilots reported similar dramatic performance improvements to those experienced by their American counterparts. The Hawker Tempest, already one of the fastest piston-engine fighters in service, became an even more formidable interceptor. Tempest squadrons achieved remarkable, heroic success against the terrifying V-1 flying bombs. Between June and September 1944, RAF 150 Wing Tempests shot down an astonishing 638 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Barry, a true ace, shot down 59 V-1s. Belgian ace squadron leader Remy van Leerde destroyed 44, and Wing Commander Roland Beaumont destroyed 31. The next most successful interceptors were the Mosquito with 623 victories, the Spitfire 14 with 303, and the Mustang with 232. The performance margin provided by the purple fuel proved invaluable in every role, from high-altitude bomber escort to desperate low-level interception. The combat effectiveness of 150-grade fuel was proven repeatedly through late 1944 and early 1945. Fighter groups that received the new fuel consistently reported increased victory claims and drastically reduced losses. By March 1945, virtually every P-51 unit was running on the high-octane elixir. Combat reports from this period show overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively. When they did fight, they usually suffered heavy losses, unable to cope with the speed and power disparity. By April 1945, missions over Germany often encountered no aerial opposition whatsoever. The Luftwaffe was finished, destroyed not just by combat, but by attrition, by crippling fuel shortages, and by the systematic, relentless elimination of its experienced pilots, who could not be replaced. On May 8, 1945, Germany surrendered. The air war over Europe ended with absolute, unquestioned Allied air supremacy. This supremacy had many causes. The P-51 Mustang's long range was undeniably crucial. American pilot training was excellent, producing a steady stream of highly skilled aviators. Allied numerical superiority was overwhelming, a tidal wave that Germany simply couldn't withstand. But the petroleum engineering advantage that 150-grade fuel provided was far more significant than many realize. The purple-dyed gasoline transformed good fighters into exceptional fighters. It instilled Allied pilots with unwavering confidence, a psychological edge born from knowing they held the superior hand. And it represented the accumulated technological and industrial might of nations that could outproduce, out-innovate, and ultimately outlast their opponents. In aerial combat, speed isn't just a number on an indicator. It is the ultimate tactical enabler. A faster fighter can choose when to engage and when to escape. A faster fighter possesses tactical flexibility that slower opponents simply lack. It can set the terms of engagement or avoid them altogether. When American fighters became demonstrably faster through the combination of excellent airframe design and this superior fuel, the Luftwaffe's tactical options narrowed dramatically, leading to their strategic defeat. The contrast between the German and Allied situations in late 1944 and early 1945 was stark, almost cruel. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and routine aircraft maintenance. German fighters often sat grounded, their magnificent machines inert for a tragic lack of fuel. When they did fly, they operated under strict fuel conservation measures that severely limited their combat capability. A German pilot who burned too much fuel in a desperate combat might not have enough to return to base, condemning himself to capture or death. An Allied pilot, by contrast, could use full power when needed, confident that adequate fuel reserves existed for the return flight. This operational flexibility had profound strategic implications. Allied fighters could maintain standing patrols for extended periods, react to threats aggressively, and sustain continuous operations around the clock. German fighters had to pick their moments carefully, conserve fuel rigidly, and often break off combat not because they were losing, but because they were running dangerously low on fuel, forcing them to abandon opportunities or risk becoming stranded. Luftwaffe pilots flew, knowing that every sortie might be their last, not just because they might be shot down, but because there might not be fuel for another mission. Allied pilots, by contrast, flew with a confidence born from undeniable material superiority. They knew their aircraft were fast, their fuel was plentiful, their support system was robust. This confidence translated directly into more aggressive tactics, better combat results, and significantly higher survival rates. The story of 150-grade fuel is, at its heart, a profound story about industrial warfare, a testament to the power of a nation's logistical and technological infrastructure. Victory, in the end, belonged to the side that could produce not just more aircraft, but better performing aircraft, not just adequate fuel, but superior fuel, not just sufficient trained pilots, but an overwhelming surplus of well-trained pilots, backed by an industrial base that could replace losses faster than the enemy could inflict them. American and British fuel chemists, toiling away in laboratories and refineries, never flew combat missions over Germany. They never faced flak or the terrifying flash of enemy fighters in their sights. Yet, their quiet, meticulous work, measured in performance numbers and manifold pressure readings, helped decisively determine who controlled the skies over Europe in 1944 and 1945. Every time a P-51 pilot pushed his throttle forward and felt his Mustang surge ahead with a surge of power that German fighters could not match, he was benefiting from a triumph of chemical engineering, an invisible force that transformed crude oil into a fuel that made the exceptional routine, turning good men into legends and their machines into aerial titans. German planners had assumed, quite reasonably, that American fighters would perform within predictable parameters based on known aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance inexplicably exceeded their calculations, sustained by a fuel production infrastructure so vast, so sophisticated, and so resilient that it represented an industrial capacity Germany simply could not counter. By the spring of 1945, as Allied armies overran Germany from east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few desperate units still flew, often with barely enough fuel for a single, futile sortie. Jet fighters like the Me-262, a technological leap forward, came tragically too late and in too few numbers, fatally handicapped by crippling fuel shortages and the absence of experienced pilots who had been systematically, ruthlessly destroyed in combat. The final accounting of World War II shows the cumulative effect of these myriad Allied advantages. American P-51 groups across all theaters flew hundreds of thousands of fighter sorties. They claimed approximately 4,950 enemy aircraft destroyed in air combat and another 4,131 destroyed on the ground. These numbers represented not just aircraft destroyed, but also highly trained pilots killed, invaluable experience lost, and German industrial capacity tragically wasted building replacements that were themselves destroyed before ever achieving strategic effect. 150-grade fuel was not solely responsible for this outcome. No single factor ever is. But it was an unquestionably significant contributing factor. It represented the crucial margin of superiority that made the difference between a close, brutal fight and a decisive, overwhelming victory. The 448 mph that a properly boosted P-51 could achieve represented not just raw velocity, but also technological superiority, industrial capacity, and scientific ingenuity. This is what German planners had not anticipated, that American fuel chemists and petroleum engineers, working diligently far from any battlefield, could create a weapon as devastatingly effective as any gun or bomb. That a simple purple-dyed gasoline could influence aerial combat as surely, as powerfully, as superior tactics or better training. That the key to air supremacy over Europe in 1945 would ultimately involve the complex compression ratios of piston engines, the anti-knock properties of aromatic hydrocarbons, and the performance numbers of aviation fuels that exceeded anything Germany, with all its scientific prowess, could produce at scale. The P-51 Mustangs that flew over Berlin in early 1944 were undeniably remarkable aircraft, marvels of engineering. The P-51 Mustangs that flew over Berlin in early 1945 were, physically, the very same aircraft, but they were powered by a secret chemical weapon, a purple liquid that made them dramatically faster, infinitely more powerful, and overwhelmingly more effective. That difference, painstakingly measured in octane numbers and performance ratings, in manifold pressure readings and airspeed indicators, was one of the many critical differences that decisively determined who would win the monumental war for Europe's skies. In that decision, in the superiority of that purple liquid pumped into fuel tanks, burned in powerful engines, and transformed into relentless, tangible victory one combat mission at a time, lay the ultimate fate of Nazi Germany and the undeniable demonstration of Allied industrial, scientific, and human might. This story of 150-grade fuel carries a profound lesson for us today, resonating far beyond the battlefields of World War II. It's a powerful reminder that in any complex endeavor, whether it's war, business, or even personal achievement, victory often hinges on seemingly small, overlooked advantages that, when scaled and strategically applied, become utterly insurmountable. Innovation isn't always glamorous. It doesn't always come in the form of a shiny new product or a headline-grabbing invention. Sometimes, the most decisive breakthroughs are found in the fundamental, the foundational, the seemingly mundane. They are in the chemistry of a fuel, the efficiency of a supply chain, the resilience of a workforce, or the foresight of leaders who invest in long-term, unsexy research. The purple liquid wasn't just fuel. It was a symbol of a robust industrial ecosystem, of continuous scientific development, and of the profound impact of unseen heroes. It teaches us that true strength lies not just in the visible, but in the entire, interconnected network of human ingenuity, industrial capacity, and scientific progress that supports it. Never underestimate the power of the invisible, the understated, or the utterly essential, because sometimes the most potent weapon is the one you can't even see.